Diagram.
Okay, welcome to class. So about Southern law, it tells us that mu naught or 4 pi integral of I dl times r bar r prime over r bar q. And where is this coming from? Basically, it tells us about a wire carrying current and creates a magnetic field. Suppose that we have two distances where this is r prime and this is r, and of course, connecting base to base, let's say the magnetic field is felt in this portion, and there is a wire. And there is, so this wire is the head, right, elemental length. And there is a current flowing in the wire in this direction. And suppose that this is the angle between the wire and this point. Then this vector is r minus r prime. Okay, call this your y-axis, call this your x-axis. And Balsabat law helps us to calculate on the effect of the magnetic field created in a wire carrying current, where dl is the elemental current, okay, the elemental length of the wire that carries the current. Okay, this mu is the permittivity of free space. It's just looking at the name, permittivity of free space is like it's a constant that tells us how much of the magnetic field can actually be permitted in that space. And mu naught is actually 4 pi times 10 to the minus 7, and it is Tesla times, if you find the unit, that is, this is R, that is meter over A, right? Right. And from there we can move to, this is A over N. This is meter. Okay. Now there are three ways to calculate magnetic field. One is to use the Balsabat law that tells us how much of magnetic field is created in wire carrying current. The second is to use a method we call adding field of known bodies, which means if I want to find the total magnetic field at a particular distance r, if I know the magnetic field in one part of the diagram or the expression as a function of r1, I can add it to the magnetic field which is r2. So if I know all the field, I can add all the magnetic field together and I will get the total magnetic field. So the magnetic field of known bodies or superposition of field of known bodies. And the third is to use the Ampere law. It says that if we are able to construct an imaginary closed loop, we call it Amperian loop, then the product of the magnetic field and the elemental length is equal to mu naught permittivity of free space times the current enclosed within that surface. And if you remember what we did when we talked about Gauss law, we say if you're able to construct an imaginary loop, okay, where the electric field is constant, then we can factor it out. In this same case too, if there is a symmetry in the current distribution, in this case, do you remember this law? This E dot dl equals to what? Equals to what? What is Gauss law? Can you remember? E dot dl is what? Is it called what? Tell me. Yes, what you're about to say is correct. Just say it. Equals to what? Is it equal to this? Is it correct? Shibushi, is it correct? Huh? Shibushi. Okay, in this case, this is the charge enclosed, but here is current enclosed. Okay, and this is the Ampere law, this is Gauss law. It functions the same way. If we can create an Amperian loop where the current distribution is symmetry, then we can factor out this guy. B times L equals to mu IA. So that B equals to mu IA over L. So it depends on the shape. If it's spherical, if it is cylindrical, that tells us what we put in. There is also what we call, if you have a magnetic field flowing in this direction, you have the current flowing in this direction, then the magnetic field will coil round in this anti-clockwise direction. So if current is going up, magnetic field will go in the positive X direction. But if it is down, if the current is going downward, then the magnetic field will go in this direction. So we need this symbol to be able to accurately understand some of the questions we'll do. Then thirdly is to use the right-hand rule. The right-hand rule tells us that the magnetic field is going in this direction. Then this is the what? This is I, the current times the L, and this is this part. So if you multiply this together, so therefore, the differential of the magnetic field is equal to I the L times R minus R prime. Okay, let's go to the first question, question 1. Question 1 says that if we are able to, if we have an infinite slab, this is Z-axis, and this is X, and let's just put some marks in between here. This is the slab. And this slab has a separation. This is minus Z over 2. This is V over 2. Okay? And that the current density is given as a function of Z, which is J naught Z squared over D squared, right? Y direction. Is that correct? So suppose you have, yes, that's correct. And now the question is, can we find the electric field? This is X. So this question is like this. It's like this. This is the Z-axis. This is the X-axis. In this diagram, it's like this. When it resets, it's like this. This is the Z, this is the X, and the Y is pointing upward. And the current density is in the direction of the Y. So if current is going this way, then what will be your magnetic field? Current is going this way, the magnetic field will go in this direction, right? Right, okay, so we can then say that B as a function of Z would be B as a function of Z going in the X direction when Z is greater than 0. But if it is flipped and the current density is not in positive Y, it's in negative Y, then the magnetic field will go in the negative X. So for BZ, so that would be when Z is less than 0, it's minus BZ SR. The question says we should find the magnetic field created outside and inside. So for the first question, to find the magnetic field on the outside, we can create an Amperian loop. That is the idea, over which the magnetic field is constant. So let's create an Amperian loop like this. Okay, call this point A, call this point B, call this point C, call this point D. Where this D is different from this D anyway. Okay, and then let's say that this is H and this is minus H. I hope you are not getting it twisted. Okay. In this case, we want to find then we write the expression. The expression of what? The expression of the Amperian law, which says if we are able to construct a closed or enclosed surface, the magnetic field times the L equals to mu naught I. So we would try to find this right hand side and also equate it to the left hand side. For the right hand side, what do we have? We have this expression over the entire Amperian loop. So going from A to B, going from B to C, going from C to D, going from D back to A. So this becomes integral of A to B of B dl plus integral of B to C of B dl plus integral of C to D B dl plus integral of D back to A B dl. So right now, I want to care about the right hand side. That's where I'm starting from. Therefore, let's say this is from 0 to L. So for the first part, for A to B, the integral is from 0 to L. Right? And this B is B of Z because it's on this X axis dot dl is the SR. Plus, going from B to C is an integral from H to minus H. And that is B. In this case, it is not on Z, it is on X, plus or minus X. And this is parallel to the Z axis. That is the Z arc. So actually you can put S arc here. Yeah, even if you don't put it, because dot product of two opposite stuff is 0. After all, it's 0 because we don't have magnetic field in the Z direction, and magnetic field is in the X direction. So plus, going from C to D is going from L to 0 of B minus Z, okay, of minus X, or to make it easy for you, just put minus B of Z, because this is and this. So let's do it properly. B minus Z minus S arc dot X arc dx. And finally, for D to A is going from minus H to H. Minus H to H of B plus or minus X dz Z arc. In this case, this cancels out, because this is the negative of the other. And then we only have what? We only have, if you integrate this, S unit vector times S unit vector is 1. I've told you before that when you dot unit vector together, it will give you 1. So this gives you what? This gives you B as a function of Z, and you are integrating over the X, which is L. Plus, this is 0, this is 0. This is integrating from, so this expression itself is what? Is minus B of Z SR dot X dx, where this and this is 1. This is L to 0. If you flip it to 0 to L, then there is minus here. Right? Because I have to change the limit of the integral. Then this gives you minus times minus is plus. This becomes plus B as a function of Z. Integral over the X is L. So this is BZL plus BZL, which is 2 of BZL. This is the right hand side. And then on the left hand side, because this is current enclosed within this loop, I need to relate that current to the current density. There's an expression that relates J and I together. If you remember, you know that I enclosed in this case is equal to the integral of J dA. Right? Now we can substitute our J. Of course, there is this. So this is this. So then the left hand side becomes mu naught this. Okay? Because it is mu naught R. But this is dA. Okay? And this will be from 0 to L over this limit, which is d over 2 and d over 2. So that is minus d over 2, d over 2, j itself. And this will be what? yr dz dx, because that is the area. the area is y is x and z. The beginning vector of y. So this is mu naught 0 to L dx minus d over 2 d over 2. I substitute my j naught which I have over there. That is j naught z squared d squared y hat dot y hat dz. Y hat dot y hat is 1. And then what do I have? I have mu naught. This directly is L. This can come forward. This is a constant in this expression I'm bringing here. I'm left with minus d over 2 of z squared dz. And this gives me mu naught L j naught over d squared. This is z cubed over 3. Then limit of the integral. And this gives me what? This gives me mu naught L j naught over d squared. This 3 is here. This basically is saying d over 2 raised to power 3 minus d over 2 or 3, which eventually gives me mu naught L j naught over 3d squared plus, no plus. This is more like d raised to power 3. This is 8. Addition of that is 4, right? Over 4. So this is mu naught L j naught over 12d. This cancel this. I'm left with 1d on top. Sorry. Right? Should be 1d on top. So if I equate both right hand side to left hand side, I have b as a function of z. 2 of that times l is equal to mu naught L j naught d over 12, right? Yeah. So this cancel this. Bz will give me for z greater than d over 2. That means I'm going to dig out of this slab. If I go in out of that slab, I have the first part, which is mu naught j naught d over 2 times 12 is 24. This is the s direction because that is bz. And if z is less than minus d over 2, it means I'm going out of this slab to the negative side. Hi guys, are we together? Is that a job, Emma? Are you here? I want to understand if I am the only one just doing my stuff or we are doing it together. Are we doing it together? Are you following? Okay, good. So what we have, this will be minus mu naught j naught d over 24 SR. Is that consistent with your notes? Check. Okay, correct, we have that. The second part is, what is the magnetic field outside? This is the magnetic field outside. For the magnetic field inside, we can construct another Applian loop inside this slab. So I can construct this, call this minus z, call this z, inside. I can repeat the same thing and call this A, B, C, D. And in this Applian inside loop, if I repeat the same thing for this, I'm going to get the same answer for the right and for the left answer. If you try it, it's basically the same. Okay? Where this integral will no longer be h and minus h, it will be z and minus z. And then eventually it will cancel. And now, if I have that, then I can, for magnetic field outside the slab, magnetic field outside the slab. What do I have? My right hand side is 2BZL equals to mu naught IE. This is my left hand side. Let's do this together. So now we solve the left hand side. That equals to mu naught double integral of j dA. Same thing. Which will be mu naught integral of 0 to L dx integral. This integral here is minus z to z. Minus z j naught z squared d squared y hat dot y hat dz, and this is 1. So this gives me mu naught times L j naught over d squared integral minus z to z squared dz. This gives what? Mu naught L j naught over d squared. This is z cubed over 3 going from minus z, right, to z. And then what does this give to us? This gives us the left hand side is mu naught L j naught over 3d squared z. Is this z cubed? This is z plus z, that is 2 of that is 2 z cubed. So that 2b z L equals to 2 mu naught L j naught z cubed over 3 d squared. Conveniently, this cancels this, L cancels L. So that I have my bz outside, inside the slab equals to mu naught j naught over 3d squared z cubed for what? For this part, right? For the upper part. That is 0. 0 is less than z, and z is less than d over 2. But it's negative j naught z cubed 3d squared for what? For 0, less than z, less than minus d over 2. Yes. Check it. Kind sharp. Should start like this. I should just say from here minus d over 2 less than z less than 0. Yeah. This way, see this way or see that way. Yes. Please, kind sharp. Take a look. I hope you get it. Okay, can we go to the second question, right? Okay, should I rub it off? Can I rub it off? Okay, second question. The second question says that we have at our disposal a number of wires, and we want to construct a solenoid from that wire. You want to construct a solenoid. You want to construct a solenoid from that wire. So let's say we have this. My diagram is amazing, so you manage to place it. Okay? Like in a circular form this way. Let's just imagine that we have that. Okay. And then I take out this outer part to be this. I have this. Where this to this is capital R. Okay? And from here to here say for example, is B. And of course, you can imagine that you have the solenoid all connected. This is going to take so much time. Okay, so we want to find the electric field, the magnetic field. How do we construct like an Amperian loop, for example? To construct an Amperian loop in this kind of setup is inside. First is inside, the second is outside. For inside, I can create another eccentric circle here and call it R. In this case, it is right to say that capital R is less than R, because you can see that this is bigger than this. But this R is less than if you had this and this together. So that is less than R plus B. In this case, I have Amperian formula over the Amperian expression over this closed loop that I've just constructed is equal to mu naught I in. And the law is that if I'm able to construct an Amperian loop over which the magnetic field is constant, I can factor it out if it's parallel to dl. Then I have B L equals to mu naught I in. This is not L. In this case, it's 2 pi R, right? Because this is, I'm constructing this shape. And I have this. And then I can put n here because I have n number of this kind of a structure. So B equals n mu naught I in over 2 pi R. But in what direction? In what direction? The way to get the direction is over which direction is the magnetic field constant. It does not matter which direction I turn this in the theta direction, the magnetic field will be the same. It means that if B is a function of, say, R and Z, as long as in the theta direction, then it does, if I turn this thing, it still looks like it's the same. It's like the flag of Japan. The flag of Japan, I think, is the only flag that if you turn it upside down, it looks exactly the same. Right? Right? If you turn it like this, it's the same. If it's exactly the same. So, no matter what the direction is in theta, is the same. So that's how I know that this is theta R. But, if I want to find the magnetic field outside, then I construct another loop outside this. In that case, I'm looking for the magnetic field here. The first, I'll see the magnetic field here. This is 1, this is 2. The magnetic field outside is automatically 0, because this is outside the symmetry. More like it's outside the symmetry. So it's outside this setup. The magnetic field outside, this is inside. The magnetic field outside is 0 because it's outside the symmetry. Please take a look before we go to question 3. Last week I said you saw something on the board, but before I know to disappear. Okay. So you see 1 0 with concentration outside.